And we have stopped here. Energy conversion or torque balance. Now, do not forget, ladies and gentlemen, there are three different words inside the machine. One is, machine is a box here. To box, you apply electric power, electric world, electric medium, and then here is mechanical output. Let's say it is motor or device converting electrical to mechanical. Here's the mechanical output, but mechanical world belongs to Newton kinematics. Here's electrical world, here's kinetical world, and ladies and gentlemen, here's magnetic medium, magnetic or electromagnetic medium. So, the rules of physics must be met. For example, in Newton's side, F equals to ma, or torque is equal to J alpha. F means total F is equal to ma. A means dV over dt. Total F means affecting minus reacting or braking. Let's say braking. Force braking. Affecting and braking. Or reaction. Action reaction is equal to mdv over dt. Here in the rotating world, we used this one because our machines are rotating. That is the total torque acting the inertia. That is the total force acting the moving mass. J dW over dt, you know. And here it is the net torque acting on a moving inertia. That is inertia. Total torque or net torque is equal to acting minus braking. Braking and J dW over dt. Ladies and gentlemen, you know that is the acceleration. You know that is the angular acceleration. Angular acceleration. So, in steady state, acceleration must be zero. You applied electric power, motor started up. There's a continuous operation in a constant speed that machine has reached. So there's no acceleration, angular acceleration change. Inertia is always positive, just like mass. Any rotating object has always positive inertia. So here is positive, something positive. Here is pivot must be zero due to steady state operation. So what about here? Applied torque must be equal to braking torque in steady state operation. It must be in balance. It must be in balance. Let's discuss the startup process. I apply the electric power and you heard such a sound. Vun, 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 vun. During that stage, startup process, you hear a changing voice. During startup, angular acceleration is positive, meaning gaining speed, increase in speed. If you hear such a voice, in such a case, angular acceleration is negative. Slow down. Yavaşlama. And then during braking, slow down. Okay. To have startup, Houston, as you see, torque acting minus torque braking must be equal to J times alpha. Alpha is positive, you see. J is always positive for any object having mass. Then right hand side is positive, so left hand side must be positive. I mean acting torque must be greater than braking torque to start the shaft up, to start up, to gain speed. It is a bit difficult. Here you see a differential equation. In fact, here is a derivative. It is a bit complicated. It is the simplest form. There will be some friction, there will be some air friction, aerodynamic losses, and this differential equation gets more complicated. So if there's a differential equation, you solve the system with respect to time. If you use differential equation, that means you want to solve out time response of speed, for example. How the speed increase when you apply electric power. Here it is in steady state. Steady state. There is no change in speed, you see. Okay, you understand the interaction in mechanical world. And due to some occurrence or events in startup process, here in this interval, there's a startup process. And then when there's a change in speed, remember EMF equation. Ka times flux times angular speed of the shaft. When there's a speed change, there is an electromotive force change. Houston, assume a permanent magnet DC motor. Here is the schematic diagram. That symbol represents the armature circuit. And here is the magnetic field part. That part represents permanent magnet. There is no electric connection to magnetic field, so flux is constant here due to permanent magnets. And here is applied terminal voltage. Let's say terminal voltage DC, plus and minus. Here you see A and B in old literature, or new one, A1, A2. In case there is nothing here, again, in old literature, you understand that it is permanent magnet motor. Now, let's draw the equivalent circuit. It looks like here's a independent voltage source, VT, supply voltage, and then that voltage is supplying the armature. Armature equivalent, you have studied this part in the previous course. Here is armature EMF, and here is armature resistance. And here is the Kirchhoff's voltage law around the loop. Applied terminal voltage will be equal to, let's say, armature current times RA plus EMF. And substitute the equation given here, Ka times flux times angular speed plus current RA, it makes VT And then here you see the current of armature is equal to Vt minus Ka flux angular speed all over array. Houston, what is the meaning of this equation? Here you see speed. If speed is smaller, Houston, electric current in the armature circuit will increase. If speed is larger, the difference here will be smaller and current will be smaller. You see how mechanical and electrical worlds interact with each other. As you see, mechanical world makes some interaction and speed is the result. Result is the speed. And speed comes to electrical world and result in some current change, electrical change. In fact, there is some electromagnetic events happening inside the machine. We will talk today. We call armature reaction. Remember synchronous machine armature reaction? There was some magnetic field interactions between rotor and stator. Again, here is a similar reaction will happen. We will talk today. And finally, there is something missing, but let me draw what we have done so far. First, in fact, perhaps you will understand better if I use transient analysis. You will not responsible. You are not responsible. Okay, I mean here's a motor DC in old style. There is no excitation coil shown in the figure. Here's the terminal voltage applied and here's armature current, and here's the mechanical world, and mechanical world shaft I mean supplies a mechanical load and there is a friction. That is the friction coefficient. Friction coefficient. I mean in the transient state everything must be defined in differential equations. In electrical world, for example, you apply a voltage source. Here is the resistance of armature. Here is inductance in transient state of armature. And here is the electromotive force induced in armature. And that is the armature current. And here is the Vt. You are not responsible in this course, but you can easily write the current in Laplace form. Let me first write down Kirchhoff's voltage law in time domain. Vt is equal to current times Ra. I prefer small caps letters because Laplace currents will be capital. And then here's the inductance, so La times di over dt, that is the induced voltage across the inductor due to current change, and that is armature EMF with respect to time, because there is an omega change, speed change. Due to speed change, there is an electromotive force change. So apply Laplace form and then take current out. Current will be Vts minus EAS over SLA plus Ra. That is the current solution in Laplace domain. In Laplace domain. You are not responsible during this course. I mean current has such a differential equation. In fact, it is implicit differential equation, that Laplace transform based on a differential equation. You see, differential equation. Here it is. Here is derivative. So, such a current solution cause current and flux result in torque, gentlemen and lady. Result in torque. I mean, torque is equal to, induced torque in electric machine is equal to a coefficient, armature coefficient, flux, and then Houston armature current. In Laplace domain, TAS, Ka times flux times IAS, due to permanent magnet poles, this is constant and this is constant. Those two makes, let's say, gamma. Gamma is a coefficient I have assigned. Gamma is equal to Ka times flux. And here it is. Laplace domain torque is equal to gamma times armature current in S domain. Okay, Houston, what I have got finally. Let me explain all those happenings in a different manner. I have applied VTS, and then here's a summation point. Here you see, that is the summation point, minus, and divided by something. Result will be divided something, 1 over SLA plus RA, and then Houston, here is armature current in Laplace domain. Here must be a armature EMF in S domain. That is the diagram for this black one. Okay, let me change color. The second one, let me change color. The second one. If you multiply the current by a simple parameter, which is gamma, you will have induced torque in Laplace domain. And then here was flux inside. It is a bit implicit. It is something hidden. Here is flux magnetic world, but it is hidden somewhere here. The magnetic field, magnetic medium is behind this block. Here you see flux. Okay, what is happening here more? Houston, torque. Torque is coming from here, mechanical world. And here's load torque. Beep, beep. In fact, we call load torque as braking torque. It is load torque right now. I defined load torque. Okay. Let's write. Let me change color. Let's write a mechanical part equation. Applied torque, which is induced torque, minus braking torque, which is load torque right now. Remember, it was braking torque. And then it is equal to J times dW over dt. That was the simple equation when there is no viscous friction. That was the equation. In case there is a friction, here would be B times W. That is viscous friction coefficient. Okay, now let's write Laplace equation. TAS minus torque load S is equal to, Houston, S times WS. That is the capital omega, you know. That is the capital omega plus B omega S. Now, that means similarly to this one. Here's coming TA, okay, and then subtract it. Here's a summation point. Subtract this guy, which is TLS. The result will be divided by 1 over S plus B S something must J. I have forgotten J. Let me complete the equation. Here is J. So here is J. Sj plus B. Finally, you have got angular speed of the shaft in Laplace domain. Houston, mechanical world in red. You see, red world is mechanical world. Mechanical world. Here is something in magnetic world. And here is something electrical world. And then, ladies and gentlemen, there is a terrific connection. I like very much. There's a connection between mechanical world to electrical world. The connection is how we got electromotive force. Remember electromotive force equation. Electromotive force is equal to, let's say, Ka times flux times angular speed of the shaft. If you have Laplace transformation, armature EMF will be equal to Ka times flux times angular speed. Bip must be capital in Laplace domain. That is the capital omega. That is ES Laplace domain. And remember, that was defined as gamma earlier. Here it is. Ka times flux. It is gamma. So armature EMF in Laplace domain is equal to, again, here's a hidden parameter coming from magnetic field, Ws. And let me introduce that purple block in the block diagram. Here's angular speed, okay, come it down and multiply it by gamma, green block, and then continue in purple. There's a mechanical world to electrical world via magnetic environment. There's the whole block diagram of DC permanent magnet motor. Here you see mechanical part, mechanical load must be here, external load, and then here's the speed. You see, if you have inverse Laplace transformation, you will have real W here, W by T, time variation of speed. If you talk about variations, you should make calculations in differential equations. That is the block diagram based on differential equations, resulting transient responses. You can calculate any time response. For example, what is the current in the blah 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 second? What is the torque induced in such a time? What is the speed after such a time duration? You can calculate every detail by using transient analysis, but it is a bit complicated. It uses differential equations, but during this course, We only deal with steady state. So you will not responsible of making calculations in differential form. Okay, I have just introduced all those different worlds, how they interact each other. Here are electrical world given in black. Excuse me, here's one more black. This is also black. Green ones coming from magnetic field, magnetic world, and again dark red is a mechanical world. Okay, dark red comes from mechanical world. I have given here some purple, but all purple written texts belong to mechanical world. Okay, that was the energy conversion. They are always together. Let me make some simulations. If here's a very heavy friction or heavy torque, there's a speed drop due to overloading. If there's a speed drop, angular speed will drop. So this term will drop. And as a result, current will increase. Houston. When there is a current increase, there is an induced torque to balance Newtonian equation. Here it is. To balance make in mechanical world. They are all connected to each other. Everyday world is very complicated. I have just shown you how it gets more complicated if you examine it in more detail. That's enough for energy conversion. Summary of energy conversion. When there is energy conversion, EMF, force, and torque operates together. Okay, let me show you what I mean. Assume that here is a generator, dynamo. Assume a permanent magnet DC dynamo. Here's the armature. Let's say A1 and A2 in new terminology. Here's the terminals and here's a load, but there's a switch. That is our load. Here is the terminal voltage plus and minus. When you apply some mechanical power into the machine in terms of torque and angular speed, here's the shaft. So you can convert that mechanical power into electric power by using DC dynamo. There must be a straight line here. DC dynamo. So let's make equivalent circuit. Here is a EMF source plus and minus. Here's the resistance. I only operate system in steady state, so I omit or neglect inductance as always in this course. And then here is the load or terminal parameters are load. Here's the terminal voltage between those two, A1 and A2. Those are in fact A1 and A2, A1 and A2. Yes, here are the terminals. Gentlemen, first, when you rotate system at a, let's say, rated nominal speed, constant rated speed, there is magnetic field due to permanent magnets. It is different than zero because we use permanent magnets in poles. Then electromotive force will be Ka times flux times angular speed. Those two are constant, making gamma. Here is W, and armature EMF. Here you see a rotation, let's say W nominal, and then that is constant due to permanent magnets. And Houston, you will have an electromotive force induced here. And across the terminals, let's say S switch, circuit breaker. First, S is off, and then as a terminal voltage, you will see or measure armature EMF. Let's apply Kirchhoff's voltage law around this loop. Induced electromotive force inside the armature will be equal to current times array plus terminal voltage. That is the generator's equation. I haven't applied some voltage from here, and that is equal to summation of the voltages all around the loop. Induced EMF is equal to voltage across this element, voltage across terminals. Yes, that's it. Houston, first S is off, so there is no current in armature yet. So apply the equation current array plus Vt. Since current is 0, induced electromotive force will be equal to terminal voltage, no load voltage. Okay. Is there any energy conversion? No, not yet. There is some energy applied to, or power applied to machine, but it is lost. It goes some friction, perhaps some other losses, I don't know yet. But there is no electrical output yet because switch is open. There is no electrical output power. So there is no energy conversion yet. Secondly, turn the S on. Houston, when you turn the switch on here in the circuit, there will be some armature current due to this electromotive force. There is armature current, and then apply the equation array I blah blah Vt. That was the equation given here and here. So Houston, there is armature current. Theta, armature current is different than 0 due to load and EMF, because EMF forces the circuit to draw some current here. That is the cause. If there is no electromotive force, there will be no current. There is electromotive force due to magnetic field and rotation. And then, since switch is on, there is an electric current. Ta-ta. Houston, multiply the equation by armature current. Armature current times EMF, RA times I squared plus Vt times I. What you see? Houston, take care. That is the electric terminal power. That is the copper loss in armature. That is the armature power, induced power. Houston, induced power. So in generator, here is induced power. you have lost some of induced power in copper loss in armature, and then rest of the power will be transferred to electrical world, terminal or electric load. VT times armature current. I mean this guy. The term voltage is VT, current is the same current. So that is the power transferred to the load. Armature power induced inside the system, somewhere here. Applied mechanical power converted into electric power. Here somewhere it is converted to electric power. But before conversion, there will be some losses. Let's say mechanical losses in terms of friction and windage. Frictional losses and windage losses we call simply in Turkish S plus V, sürtünme vantilasyon. Please do not forget. You will generally see PSV in solution papers, solution sheets. But in exams, if you use mechanical losses or friction and windage, there is no point, nothing wrong. Here's mechanical losses. There will be some core losses, but we generally neglect core losses. We add core losses into mechanical power. So let me make it more clear. Here is applied mechanical power. Here is mechanical losses. And here would be core losses, in armature especially, and pole tips, core losses. But they act as if they are mechanical losses. So generally added into mechanical losses, just like what it was in synchronous machine. They are generally given in mechanical losses. They give no emphasis on core losses. And of course, core losses much more smaller than AC machines, because in AC, you know, there's a time derivation of magnetic flux in every part. So that changing magnetic flux will induce core losses. Excuse me. But here in DC, especially in statical parts, stator and pole body, there is no changing magnetic field. So statical parts cause no core losses. Total core losses are much more smaller than the losses in AC machines. So we generally not deal with core losses. We give some mechanical losses. Always add core losses into mechanical losses, and then we simply express the diagram like this. Mechanical losses in terms of sürtünme ve vantilasyon, windage and friction, wind. Armature power, that is the induced or converted power. And then here is copper loss in armature winding that heats the armature. Here is the electric output. That belongs to dynamo operation, or generator, generator operation. In motor operation, you apply electric power. Some of the electric power applied will be lost in copper losses in armature. Rest of the armature power will be converted into mechanical world that is called as armature power or induced power, converted power. Some of the induced powers or mechanical powers converted in the armature will be lost in mechanical parts as sürtünme ve ventilasyon. Rest of the mechanical power will be go out from the shaft or net mechanical power. That belongs to motor operation, the similar diagram, and we call power balance or equilibrium. Power equilibrium. All powers must be in a balance or equilibrium. Okay, ladies and gentlemen, we'd better give a 10-minute break to get relief and then come back. Break, let me write here, break till okay, rest a bit. Now we are together again. Let me complete some of the missing points I have done from the previous hour. In fact, such a diagram belongs to such a connection. If there is a connection change, the equations, differential equations, the relations, the connections, and the block diagram will vary, will be changed. It is not a fixed block diagram. And again, for easiness, I only used permanent magnet DC dynamo or motor here. So relations a little bit easier in case there is electromagnet in poles, the connection will cause some different equations. For example, let's say there's a field coil having a resistance of RF, and where it would be. It is something together with this, a new parameter. I don't know yet how to include field resistance in the equations. And then if there's a field resistance given, there must be a field current square times RF, copper loss in field coil, ladies and gentlemen. So all those diagrams with respect to change, with respect to connection of machine. So here would be Let me draw copper loss in field. I don't know exactly if it is or not. It depends the connection. Copper loss in field coil. That is the diagram must be evaluated, must be comprehended. First of all, as an engineer, we always draw connection diagram. We make equivalent circuit. We apply Kirchhoff's voltage law and the equations, and then decide where are the losses, where are the currents or powers, what is the balance. We all construct those relations after a given diagram. After, for example, I will clean, let me open a blank page here. For example, I will delete this page right now after discussing. Let's say here's a motor, and then here's a shunt winding. I will talk in the next hour. Here's a serial connected field, let's say shunt serial field coil, and then here's the terminal voltage, plus and minus. You apply electric power, you convert it into mechanical power. But Houston, as you see, here are new parameters. Loop equations will be changed. What is the EMF? Excuse me. Excuse me, I am sneezing all the time. In this morning, I've got an allergic body. Here's a weather change this morning, so I couldn't get used to leave that change right now. So I get allergized and sneezing. I'm very sorry about that. Perhaps I will keep the course shorter. I'm not sure yet. Okay, as you see, we always draw diagram, and then consider where are the currents. That is the load current, that is the shunt field current, that is the armature current. You see different colors, currents, perhaps different equations. Everything will be changed. First draw the diagram and then apply Kirchhoff's voltage law, Kirchhoff's current law, then write equations, and then make calculations. All those discipline must be conducted. Otherwise, you will memorize a solution and you will fail in exams. You should draw the diagram first. Okay, that was the power balance. Here will be, excuse me, here will be some copper losses in the field winding. Okay, that's it. Here will be some core losses. Here it is. Core losses, iron losses, I mean. Here it was, core losses. But we generally give all of them in mechanical losses. Okay, that was the power balance and energy conversion issues. Okay, some more. Let me add another perspective related with energy conversion. I used motor. Generally, in motor, you see electromotive force here, this element. If increases, current will drop. That means when you gain speed, current will be down. Excuse me, let me write it down here. Current, first it rises and then gets smaller. That is the current armature. Green one. Current will change. In some books, EMF inside the motor called as back EMF. Back EMF. Türkçe'de zıt EMK diye söyleniyor. Back EMF. Ya da counter EMF diye de geçen kitaplarda var. Counter EMF. Back EMF. Because it makes a counter relation. For example, if EMF gets larger, current will increase. Current will increase. Excuse me, decrease. Because here's the, let me write current. Current is equal to VT minus armature EMF over array. If this guy increase, current will decrease. Here's the delta voltage. That is backing voltage. In case there is no rotation yet, speed is 0. In such a case, here would be 0. And the current will be startup current. Start up. Yol verme. Come on. Because machine needs much more current, torque to start the load up. All the relations are behind these equations.